Okay, good morning. Welcome back. So today we are going to have lecture number 7, talking about classification. So this is the most important and widely applicable approach in machine learning. And you will see a lot of examples in the real world today using classification to do a lot of different things. So that's a major area for AI. However, I would like to tell you that this technology has been poorly applied to single cell study because you don't know how to obtain the organized training data. So in biology, and there are very few ground truths. So you know for sure, okay, this cell type supposed to be subtype or whatever tissue you think should be right. And traditionally, you may have some marker genes, but that's not for single cell data. It could be antibody and stain for flow cytometry. And some of them just not apply to single cell data at all. So a lot of pre-knowledge will not be applicable here. So we will have some issues. But as a class, so I have to teach, to mention all the classification algorithm. Otherwise, we cannot call it machine learning related topic. Okay, so it's such an important topic in machine learning. All right, I will go through some of this common algorithm in classification after I discuss the definition of the classification and their position in AI or machine learning or pattern recognition. We will go through neural network, KNN, and K nearest neighbor network, logistic regression, LDA, naive Bayesian, and then we will mention how are you going to evaluate whether your classification algorithm is good or bad, the performance. And finally, we will mention the classification tools in single cell identification, single cell type, basically. At the very end, I will illustrate the manual annotation, and although we have those classification algorithm help us, eventually the current state, the state of art of annotation has to be done manually. That means you have to select the marker genes and process the information based on your domain knowledge, and then decide by yourself. Okay, so what is classification? This is a procedure, it's a process that predict the class of given data points. And this is a supervised learning procedure because you have to train your algorithm first. When you train your algorithm, that means you use training data set to teach the algorithm. The algorithm will reset its parameters based on the provide training data sets. And then after the parameter is set, then you can use this as a classifier and then apply to real data, okay? So that's very different from clustering algorithm. Clustering, you don't have to train your data, you just tell the clustering algorithm what numbers of cluster you expect to see, and then in your homework is you define some parameters, but that's a global level. So you say, okay, what's the cutoff as an outlier, and then you will automatically allow the algorithm to find the cluster for you. By the way, your homework is still due, and you have explain PCA. A lot of you have not sent me video. A small penalty will apply, but it's still good to send me the video, so I know you can use your own language to explain PCA. If you still have difficult, maybe revisit the video, the lecture recording, and try to figure out, or you can come up and show off in the office hour, and we can go through together again, okay? But it's better you still don't give up. Use a couple minutes to explain PCA, and also your next homework I post in the Google class is to explain that algorithm, or the DB scan related algorithm, to select the cutoff, right? The parameters, the paper you have to explain to me. Okay, as I said, it's a two-step process: training, and that's a learning step, and then apply to real data. So you have labeled training data, okay? For example, you have green cell, red cell, and their gene expression profile, and that's features, variables, and you have to give to the training procedure. Then sometimes you need a feature extraction, because otherwise it's high dimensional data. You may learn some features out of it to get rid of some noise. And these major features will be used to train the algorithm. So the vector in the middle here, we know vectors are the data points, okay, in our case. So you use these vectors, and also these vectors, each data point is labeled with either red or green, and the algorithm will be able to adjust its parameters internally. And then once the procedure is done, you have the metrics to test, okay, so-called cross-validation. So we will go through that procedure. And then you see your classifier is trained, and it's when applied to training data, you have accuracy of the classification, say 85% of accuracy. Then you are satisfied with this result. You are going to deploy your classifier to real application. Now you have new data points comes in, and then the classifier will tell you whether this is a red cell or green cell. Is that clear? So mathematically, abstraction is you have function. So this function will take your data. In this picture, and the data is apple picture, tomato, or cow. And then the function will take that. You can subtract or learn the feature of this picture and price that into a vector and give the function. So function will just calculate and give you the label. Because it has already been trained, so it knows how to take that input image and process it through this network of parameters. There are functions in there, and to compute give you the value. This value will be the labels. All right. Okay, so we call this function the prediction function. And then you have input X and your output is Y. When you do the training, so you don't rely on a small number of training image here. So you have to have a large set of data in order to let the predict function explore the search space. The function has seen this, a lot of different data points, and then it knows the answer. So until then, you will be able to give the test image. So we put an apple image here. The feature will be learned and go through the parameter space, and the function will give you the prediction. Okay, so that's the framework. Now, the question is about F. So F, you have, depends on your algorithms. You have different kind of F. all right? But this framework, just like that. Any questions so far? Online students? In-class students? Clear? Easy? Okay. So we will discuss a couple of these classifiers. In this class, I will mention logistic regression, which just very simple, a logistic curve function, and the naive Bayesian classifiers, okay, just like your in my toolbox, actually, this cell type identification use this naive Bayesian method as a background. We will mention perceptron. Perceptron is the neuron. So when you're talking about neural network, perceptron is a unit of the neural network. It's a single neuron. Let's see how it's defined in this vector space, and how I will show you how exactly this it looks like an operation, and it's aggregator, and aggregate all the input information signals, and then sum them and weight sum, and then give output. So if you have a lot of perceptrons connected, it forms a network. This network is a neural network. Next class, next week, we will talking about support vector machine and the decision trees, or something else is on the right side of this. Okay, neuron, perceptron. I think we roughly know, and we think we know how in biology, neuroscience, how neuron works. And this is a picture of hippocampus neuron, and they have a lot of connections, and then signal comes in from this axon, then will process in there in the neuron, and then the electron signal will pass on and to give you output. So let's just focus on this single neuron, and then see how this form the basic foundation of the whole neural network. So we can consider perceptron as this, in this symbol here. You see this a sum sign in the middle, because the function of this is just take input. So if you think this neuron has a lot of inputs, and in this case, we have 4 inputs. The inputs are the numbers. Okay, we can consider this as a vector. So you can have a 1×4 vector here, and each numbers in the vector is a piece of signal, input signal into that neuron. Okay, so if you have a weight matrix, for example, as a 1 across all the weight with W0 is 1, W1 is 1, W2 is 1, so this like this unweighted. So all the neuron will do is to take a sum of the input. So your input x1, x0 in this case is 1, x1, x2, xm will be summed together. If you put a weight on it, so each input value will times its weight before sum together. Okay, that's all this neuron will do. It takes information and sum it, and then give out. The total will be passed on to the next. So the output will be here. So before you send the information out, you can have so-called activation function, because we know that simulation of neuron, the neuron is not take every information in and pass out. It has to have some threshold of you have to accumulate enough of information before you send out the signal to pass on to the next level. To simulate that, so we have activation function. This function could be very simple. So after a certain threshold, we will send out the message. Otherwise, it's lower this than threshold, then we just keep the output as 0, right? So that's a basic definition. So I'm going to show you an example and see, once we set up this, how can we train the neuron using different inputs and adjust the weight matrix, vector, so to make this neuron work as we expect it to. I'm going to use whiteboard, blackboard illustration to do this. You have the same picture in your next slide if you decide to go there directly. So I'm going to draw a neuron on the so once we've, so this is useful once we have, so I try to make this close to the microphone so people, Okay, so we have neuron, so this is it's aggregation machine, so operation information in there. So for example, we have 4 information coming in for. Okay. The first time we have input as 1, and it's -2, 0, 1. So this is a vector and it's abstract, but you can think about any information you can encode those into a vector. It's a data point, right? So what we expect from our training is for this particular neuron, we want to have this input and my output is -1. So that's my expectation. So that's my first training data. Okay, I try. And then in this case, you have a lot of different options for the weight here. I see this weight 0, 1. People in computer science like to use 0 as the starting of the index, and they insist on that. I'm not a big fan of that. Okay, anyway, so we have W0, W1, W2, W3, okay? So we can put this as a vector. So for example, this will be a vector. So for example, just 1, 1, 1, 1. I initialize the parameter for this neuron without any power, actually, no weight. So what I can do is to this 1 times 1, 2 times 1, 0. So what's the outcome? I do that. Basically, I sum them together. 0, yes. So that's my 0. It's not what I want. Okay, not good. So I have to change. So let's see if I give some weight. Is that better? So for this training data set, if I give weight W0, W1, W2, W3, this value, it works, right? And so on. Okay, so that's good. So I train my neuron in this way, satisfied my training, and it's good. So I can accept this. However, the training should be more comprehensive. So I input another 0, minus 1.5, that's 0.5, minus 1. If I do this, still okay, right? Still okay. Output is 0, minus 1. If output. So this vector still works because this is only a sign. Either positive or negative. However, if I try the third one, so the third one output will be 1. Minus 1, 1.5. Now in this case, this doesn't work. Yeah.
For the second one, are you getting it to -1?
Yeah, because the output only is a sign here. So if it's a positive or negative, become either +1 or -1.
But from the weights of 1, 1, 0, 0.
Yeah, from this, if you set up this, so that will be -1.
-1.5.
Yeah, because here we have a sum function. If
we're
this,
adding it to the first vector.
yeah, so for the right input, okay. So if you type this will be 1. Oh, so this will be 0, right? Yeah. This will be -5, and this will be 0, 0. So the output will be -5, -1.5. It's negative, and this sum function will give you.
So are we giving it a yes, no?
Yeah, yes, no. So the
Okay.
output is binary.
Okay. got it.
Yeah. It's binary.
And are we just saying it's non-zero when we say yes?
That's right. So this just made up a function.
Yeah.
So you just, if your total, the sum is positive, okay, 1. If negative, -1.
So if the sum is 0,
0 will not be in there. So we don't have training data as output as 0.
okay.
So this vector has to be satisfied all this. So this will not work. So this not work on the third training.
Okay, I see.
So this is not a good solution. So we need to try something else. Maybe you try -1, not working. So we have to reset those parameters, and one of these combinations will be 0.7, 1.4, 0. So this sum function is if give you either +1 or -1, depends on your output to y. Okay, so this procedure, so this you can test, you can try, and this vector, this W0 is negative 0.7, another one is 1.4, another 2, 0, another 3, 0.7. So this is a solution which to set up the parameters for this particular neuron, and will make 3 training data in the correct answer as we expected, because we know input green will give you -1, in red will be -1, input yellow will be 0. This is only 3 data set training data points. You can have a lot. So once you have a lot, the parameters you can choose will be more specific.
Okay, a -1 on that weight for the first weight.
Negative this,
The first weight, first set of weights.
this one.
1, 1, 0, 0.
Oh, this side will not work.
Right, but I'll just add that a -1.
Yeah, yeah. Yeah, you can put anything, but this is just an example that this is just an example by an example.
Yeah, I'll just,
Not working.
are we not multiplying them together? Or are we?
No, this is one solution. One set of solutions.
Right, like, I was wondering for the math, are we not multiplying the two vectors together?
Yeah, we actually will. For example, you have input here.
Yeah.
That's your V, so the V1, okay?
Right,
So that's your weight matrix.
Right.
All you have to do is dot product. V1 transpose and times W. It is dot product, and you end up with one single number. A single number is sum of this. So if you transpose that, so that becomes 1, 2, 0, 1. Right. And times this vector.
yeah.
Comes this vector here. So the way I want to use for product. Okay, I don't know value here. So then this value will be passed with the sine function. Right. Give you that. So again, internally in the neural network, it's dot product of the input with the weight. Okay, yeah.
I'll just wonder because the first set didn't look like it worked for the red or the green numbers. Because it should be a positive one with the word green.
Let me see my example. And this comes here.
Oh, it was the green times the first one. The first one.
Green times. Oh, this one doesn't work. Yeah. So that's a by the example. I just tell you, you can have a random guess, but this doesn't work. This is one of the working example of the site of the weight. But in this small example, you should have many different solutions. Okay, so this is a very basic single neuron, and its core is this dot product of input signal times the vector of weight. And then variation of neuron is how you set up this, and also how are you going to use this function. So this function in this case is very simple sine function, but you can make this more complicated in better activation. Okay, so that's gave you different flavors of what type of neuron it is. Okay, on your screen, you have this example, and on the right side of this is the MATLAB code. Okay, my first set of parameters, that weight of the neuron, the weight vector is this W0, have 1, -1, 0, 0. And this one example that doesn't work for this 3 input training. But W1, this vector is one of the examples that works. Okay, V, this is my input vector. And because I have 3 training data points, so this is a 3 by 4 matrix. But because I want to just give one computation and get everything, so I put the training data points into a matrix. So it just do one multiplication will work. And that's, so each input data contains 4 signals weighted differently. So you have different values. So I can multiplicate this matrix with either this one or that one. But I decide to put them together, so I have just one-time multiplication to the 3 training data and I get my results. Okay, the first row is the results I get using the first weight site. And the sign is +1, +1, -1, which is not what we expect to see. And the second one is the sign as -1, -1. Okay. So in this case, we will see, okay, W1 is the site of the parameter. It's good for this 3 training data. Okay. Again, in the center is just a dot product. Okay, so that's another way to illustrate. So you see different kinds of this type of the illustration. And again, always found this aggregator. So the center is the sum of the information from different inputs. And you have to multiplicate the input signal with its weight and aggregate. And then the function is activation function in the expression of that. This is the dot product, right? And the result of the dot product gave to the function, active function. So active function can be this logistic. Okay. Simple ones. This rectified linear unit, that means if your value is small, you don't change the output, still 0, but after the certain threshold, the output, the strength will linearly proportional to your value of your dot product of aggregation information you get. And there are different this rectified linear unit and the different flavors of this. Okay, those are the common ones you can choose from. Sigmoid function, which is the first one I show you here. I just think this is like a soft cutoff. If you have a hard cutoff, that means you at a certain level of the threshold, so that's in the middle here. Then you have a sudden jump. So that is the function of the hard cutoff. You will be either +1 or -1 or 0 or 1, depends on whether your value is greater than this cutoff or not. Well, this logistic regression, logistic curve just gave you a soft boundary, so you can see, okay, in the middle here, I have 50-50 chance to be either +1 or -1. Well, when you move to here, you have 80% being +1. To give you the buffer here. And these two expressions are the same, because if you do, if you transform this to EX 1 over it, and this will be transformed to EX 1, and then into that. So this is you can express in either way. I think this is the more intuitively right, and it's a ratio, okay, ratio between exponential of your x divided by 1 plus exponential of x, whatever. All right, so that's the hard cutoff. That's what we used in on the blackboard here. You have a sum function. And the boundary, the threshold of here is 0. Okay, once you have greater than 0, then you have +1, otherwise a -1. If you choose active function using this linear regression, then again, the output will proportional to the sum, the total of your aggregated information. Yes, Alex?
So all the aggregation functions are supposed to be binary, right?
No, no, in this case, for example, you can output the result of your regression depends on your slope. So in this case, it's not the binary output. In this case, it's also not, because if you think this is +1, that's -1, you have somewhere in the -0.2, +0.3, you still have this continuous variable. Okay, so hard decision, no decision, soft decision. All right, so if you express this out, you have dot product between your input vector x and you parameter, the weight vector, so that's dot product. And this expression, if you look at this two-dimensional example, is actually a linear expression. So you have this line here, and if you output is above this curve, this line, it's one of the class, otherwise it's another class. So this, for this simple, the single neuron operation, you actually create this separation between your training data points. Okay. So this function is just internally it's straight line here. Okay. Okay, on the blackboard, I just showed we have two different set of parameter solutions. One will be okay, another not working. So how can you get those parameters, the values? Optimization certainly is an option, but optimization, the optimizer, is a huge investment. So computationally. So people use this kind of a shortcut instead of using to borrow. You don't want to borrow a nuclear weapon to do something all the time. So do this using this shortcut and lightweight procedure. And you see this norm that's compare between the parameter settings. If there's no change, then we stop searching. Then keep updating, depends on your training results. So this procedure will help you to find the solution of this. Okay. Next, we are going to connect one neuron with another. Okay, let's see. This is a neuron we just showed as an example of single neuron, right? It has 3 inputs, 1, 2, 3. And it will give the output, which is this. Is that okay? Are you with me right now? So we isolate this out, this particular neuron out. That's what you just saw in previous slides. We have 3 input. Of course, this example has 4 inputs, but it's the same. So 3 inputs and then weight vector and the dot product. In the same layer, you have another one. Exactly the same, repeat. You have another one. So in this green layer, you have 4 identical, you can initialize them as identical neurons, make an array of neurons. And then you add another layers, the orange layers in front of it. The input for orange layers is not shown out here, but you can have other input here. Or you can use this as the 4th layer. Then the input will be the data you're collecting. Okay. And then you have some kind of process, and then you start to shoot out your output and give to over the next level. So next level, you have 4 neurons, then you have duplicate your output and into 4 different signals and give to the neurons. And all the parameters here will be trained 1, 2, 3, 4. This W1, W2 will be trained independently or trained as a group. I think it will be trained as a group, okay? Because you have to keep adding layers and output, and at the end give the output. So at least right now you know how to connect one neuron to another and make multi-neuron layers. So once you have this basic foundation, you can add up, okay, make a lot of them. You can change the number of neurons in each layer. You can have small numbers of neurons in one layer and suddenly expand it to a lot, and then shrink and then expand again. So in this procedure, and information gets encoded, decoded, compressed, but whatever, you pass on this information signals from one layer to another until the end. What you can change are those weight parameters. You can change the structure of this organization.
Decompress the data or only compress it?
I think this, in this case, is called deep. You expand the individual signal into a more. So in this case, you make a information which contains in 3 neurons into 4. So you actually decoded. You think in your signals there are information that can be expanded. Then in this way, you expand it. So for each neuron, I have input. So for example, for each neuron, I have input from A, B, C. So that's my input, right? And then for my neuron, I can do this product, inner product with that. For then give me the output of this. And I can do the same thing. And because each of these green neurons receive the same input, so I don't have to do independently the input. So I just use one set of input as vector ABC and multiply by its corresponding weight and get 4 numbers here. So that's my Y1, Y2, Y3, Y4. That will be the values for Y1, Y2, Y3, Y4. The values of those neurons aggregated sum, and that's the information will be passed on to the next level. You can add active function in between. Say I want to change the threshold or have a soft cutoff, allow my information to pass on as a 0 or -1 or +1 or some other values depend on my active function to next level. Again, in the center of this aggregation procedure is dot product of your weight matrix with your input signal. Yeah.
All your inputs are the same.
That's right, because A value, once it's computed, is copied to each of these. Yes, so input is the same for all the 4 neurons in there.
So A is like equal to 1, and then if you travel to Y4, you're just moving, right?
By different weight, yeah. So when you pass on to the first neuron, green neurons, you have to multiply this weight.
Mhm.
If you travel to the second neuron, and you weigh by this value, so the weight will change. So depends on your setup, you design different neural networks. This is called a single layer neural networks. Okay. And I think that's in the early stage, you don't have enough computational power, then people use this a lot and then found that's like Pioneer works, and then found it's not very good and useless. So in the computational area, and people experience this so-called neural network freezing period. This in research application, there's no research, no application until you have enough CPU power and memory, then you can start to design multi-layers and also deep neural network. Deep neural network means you have many, maybe hundreds of layers. I don't know exact number, but people found those kind of neurons, if you train with a large data set, performance really well. So that's why we see so many real world applications right now. And also the industry has gone through this freezing period in the cold period of time of the development of neural networks. Now it's becoming widely applied. As I said, it's you can use this to do encoding, decoding, and people find a lot of applications in there. So you have input. So now we put this instead of horizontally, we put it vertically, and the input is in the lower part, and then you output it on the top. But the same idea. The idea of autoencoder is your hidden layer has much smaller neurons compared to input and output. So through this procedure, and you actually compress the information, so-called encode, and then you can decode it. So in this case, if you have input data and then go through this, you want to compare it out. So you want to compare in and out, and change the parameter in middle, make them as close or as similar as possible. So this is so-called self-training, and you use your own data to train the parameters and get a similar output, and then you are ready for other tasks. And people think this is not a supervised algorithm. This is called semi-supervised or self-supervised. Another is this convolutional neural network. Okay, the special thing about this is how are you going to encode your picture image or any input data in the matrix format and aggregate or convolute this information and project to the next level. So I'm going to play with this video and to illustrate this point, and then we take a break. Okay, so for example, you have a cat, a dog pictures. How are you going to convert this picture pixels into something you can use as a training? Okay, so one simplest way is just you have a matrix of the picture, and then you cut each vector and concatenate into a long vector and give to neural network. It will work. The convolutional neural networks have some other ideas. It start to do some kind of sliding window, small sliding window, or maybe in different size and across all the picture of image, and then aggregate information and project into a new so-called feature map, and then process this as a downstream. So I think this picture, this video is really good to illustrate that. So let's see. It's silent video, so you can just see, okay, I have a picture, have a character in there. So this sliding window scan is just 3 by 3 small matrix and through all the large picture and sum the information and the project onto a new picture. There are some kind of boundary issues if you run out of so you have to add some pixel and then allow this to cover the whole surface. But that's a trivial technique. Okay, so that's yeah. Okay, go back. And to learn this feature map and then summarize your picture into this Python and then compare with trained patterns and then match with A and 92% of confidence, then report the picture contains A instead of B, C, D, E. Okay, 5 minutes break. All right, just a brief announcement. This summer, and my student, Christine Bechara, and I will teach a new course. This is a summer course, only maybe just 1 credit, computational quantum computing for life scientists. So if you are interested in and keep doing this, we will be in the same room here and talking about some of the topics, very basic, but eventually you get the idea how this quantum computer will work. And we do have some applications at the end, which apply to single cell gene regulatory network simulation using quantum computing. Okay, come back to the slide here. So you see this procedure is just scan through the large picture and using this, what should we call? It's a small window and to scan the picture and to summarize the information to give you the convolutionary feature map, and then using these presentations to do the downstream clustering. And they're in the middle, they're called, this object is called convolution kernel. So next lecture, we will briefly mention what a kernel is. So this is like a filter, and then to allow you to go through this filter to compute new values for the source pixels you aggregate the information from. Okay, so when you have a neural network have a lot of layers, then we call it a deep learning neural network. There's no fundamental difference between neural network and neural network based machine learning and the deep learning, they're all the same. It's just scaled up and the performance really get improved. In the same time, you have to have a suitable hardware to support this deep learning neural network. Okay, so we jump out from neural network stuff and move to another simple classification algorithm called nearest neighbor. K indicates the number of the neighbors you want to consider. It's pretty easy. You have to know how to project your data points into certain space so you can compute the distance between data points. So you will have a setup. In this case, have a yellow and purple two class of data points. Then your test data point, which is indicated by this red star here. Then you will compute the distance between your red star to its neighbors. And then you have to have a parameter K, see how many neighbor data points you want to consider. If you decide to consider only 3, then you will look at this region, count 3 neighbors, and then count. Within the 3 neighbors, you have 2 purple and 1 yellow. So you will assign this new data point start as a purple class. You vote by the majority. When you consider K equals 6, then nearest neighbor, in this case, you have 4 yellow points as a neighbor, with only 2 purple points as a neighbor of your testing data point. In that case, you will classify this new data point indicated by this red star as a yellow class A group. That's it. As you can see, underline this algorithm, you still can rely on lineage algebra. You know how to compute the distance between data points. That's the key. Once you have that, you have a label because you label class A and B. That's a training data. You know their class and you're testing just based on the distance between them and their neighbors and vote. You can introduce some kind of variation and in there. The way is to weight the distance. You can weight the distance. For example, this distance is small, you can have a bigger weight. Okay. So emphasize the close neighbors, whatever. And that's just some kind of a modification and may improve your results. And this simple algorithm called lazy learning algorithm because, well, it's just very simple and easy to do. Another is logistic regression, and you have already seen this logistic function before, that's soft cut. And you can use this function to assign the membership of the testing value. That's your training data, blue and yellow, and you construct this logistic curve function. This function need a parameter, so you know the center of that and the shape, how widespread or very steep jump. So that's based on the parameters of this curve. So once you establish this curve, you can start to test your new data points. If your new data point is here, and then it has a certain of probability belongs to which group. Okay, next. This is called LDA, stands for linear discriminant analysis. The center of this algorithm is PCA. Well, this PCA is different from your dimensionality reduction PCA. The purpose is different here. But remember, if you, I hope you did your homework, the regular PCA is to reduce the dimension or found the way to display your data point as dispersed as possible. Here, the purpose of this PCA in LDA is to found a projection of your data point so that the two labeled group of data as separable as much as possible. I will use examples to illustrate what I'm talking about here. In 2 dimensions, and you want to find a projection, which is just aligned to project your data on it so that the data can be separated. The red and the green can be separable. Of course, on this example, it's not a good projection. The best projection will be, to me, it will be some this direction and the data projected on it, so you can separate them. If you have high dimension, then the same idea. And if you have a 3 dimension, then you want to find a first and the second components to form a plant. So data projected on them are separable. And how can you select the best projection? So best axis, new axis. In this example, you can select this one, and that's original. So you separate you project your data onto red one here, blue one here. They are separable. And then you can select another. It's still at the most separable projection you will get will be this one. Okay. So if you look at this more carefully, you will see, okay, the mean of these two becomes largest. That's the best, right? You want to find a projection so that the mean of the 2 group of data onto the projection, the distance can be as large as possible. Well, in another suboptimal solution, the D, this D will not as large as the optimal solution here. Okay, if you think of a teapots, you have 2 teapots. Instead of display the teapots as their most variable data points onto this projection of the picture of 2-dimensional picture, you want to find an angle which you can separate these 2 teapots as much as possible, right? We come back to the first page, this illustration. If you don't do anything, you just use original coordinate system to project these data points onto the x-axis, then this is again not the best solution because the mean in the center of this red and the green point are not difference between the mean of two groups is not the largest. Well, the algorithm also not only consider the difference between the mean, green and red, and squared because you have a positive and negative value is squared. It's just a difference between them. You also consider the variance within the point, within the group, the point within the group. So you want to consider the variance among right group points and the variance among the right group points. And you take a ratio, you want to sum this variance and take a ratio, and you want to maximize this. Maximize this value. Maximize means you want to separate the mean between these two groups. At the same time, you want to, the variance within the same group data points shrink as smaller as possible. This is extreme example. So you have the best solution along this axis from the left lower corner to the upper right corner. Instead of, this is not the best solution. The best solution actually is from the left top to the right bottom. So in that case, the ratio becomes the largest rather than this. Okay. Although in this case you separate them, but the variance between each group is too large and over compromise your difference between the mean you can get. Okay, yeah.
In order to minimize the variance within the group?
Within the group, yes.
I thought you would want to maximize the variation.
No, you want to find an angle to minimize it because you want to the same group of data points to cluster together and separatable from the other group of data points. So how to do this? You will find some familiar equations here. Let's first look at the number 5. So this step is eigendecomposition. Eigendecomposition on matrix in this form. So these two matrices are the would see this called it's not a covariance matrix. This scatter matrix, something like this. S. Okay. Let me think about whether we should call this covariance matrix or not. It's not a covariance matrix. It's like a distance matrix between data points. Okay. You consider within the group pairwise points with that group. And also you will consider a pair of every pairs of the data points with cross group. You have a red group 0.1 and the distance to green group 0.1, red group data point 1, green group data point 2. So something like this. So you have two matrices. Two matrices, one is within the group distance, and another is without outside between groups. And then this will help you to find the projection, which the best solution for take consideration of all the difference between the mean and the smaller, minimize the variance within the group. Yeah, so this full implementation of LDA in MATLAB, it's just this. I think that matrix is within group. Let me see how I compute it within. Stop it. And then that's between group. Okay. So the difference between PCA, LDA. LDA deal with labeled data. If you don't consider labels, and then you just project the data and found the principal component, component or the projection of the axis, then you try to maximize the variability. Well, LDA, you consider the separation of the data. So that's the mean difference between two groups, and also consider the within group variability. Any questions? Okay, we are moving on. Naive Bayesian, and that's a formula, Bayesian's formula. You can use this as a, you can use this idea as a classifier because you consider the prior probability. And putting that here, and then there's the likelihood, and then you compute a posterior probability. I use the example to show you here, and in this setup, you have prior probability for being yellow. You have a total 17 points, and 7 of them are yellow. So you have a prior probability for a newly introduced data point to be yellow because the frequency in the population is like that. So it's more likely to be a green one because within the 17 examples, 10 of them are green ones. So if we don't consider anything else, these new data points are likely to be green, right? So that's a prior probability. And then we will calculate the likelihood being, if the green, in this case, we consider a local, neighbors. Then for this, yes. Yeah, by looking at close neighbors, 4 of them, within the 10 green one, there are 3 to be neighbors. Will in 7 yellows, only 1 being neighbors, being the neighbors of new data points. So you have a prior probability times this. So that's your posterior probability being green, and that's your posterior probability being yellow. And at the end, I think this value is greater than that. So this new data point is more likely to be green. So you compare at the end the posterior probabilities. That's another example. It's more closely to single cell. For example, you have two type of cells. One is green, one is red. So I'm translating this scenario into single cell study. You have a classification of a green cell, red cell. They are defined by those marker genes expression. If you see, okay, money, three, the marker or highly expressed markers, then this could be more likely to be a red cell, where you have marker gene, the dinner plants. This could be a green cell based on your dictionary. Well, when you really observe your cell expression profile of those marker genes, you will first have a clear probability for being red cell or green cell. Then you have this likelihood that you compute the posterior probability of being. They also consider the frequency of these keywords actually in real computation. So if you have time, you can go through this table and try to see how this different piece of these fragments of probability put together to compute this posterior probability. Exactly the same idea was built in my toolbox. I have a database where I have hundreds of the cell types with their marker genes, and I will have this tables and frequency of my marker genes appeared in my whole database. And then once I have an expression profiles, I will compute to search for the marker genes expression level and compute a likelihood of being certain cell types. And then I will report, see, okay, what's the most likely cell type for the cell I observed or cell group I observed? What's the second most likely? So I have a list, so you can select different cell types. If you don't select manually, I will just give you the top hit. Okay. There are other papers, books you can use as a reference. Okay, next I'm going to mention how are you going to evaluate the performance of trained classifier. So as we described, some classifier you don't need the training. It's like a KNN, you just directly found the neighbors and vote. Some need the training, whatever. Once you have a classifier after training, you want to see, okay, how good the performance is. And then you have some idea the confidence of the application for this. So the technology we can use is called, there's several of them. They're called cross-validation. You can compute precision of the recall based on your training or test. Or I don't know how many of these you have used ROC curve, the receiver operating characteristics curve. Any of you have used ROC curve? No. Okay, we will mention that. Okay, so cross-validation, you start with your training data. As we said, we expect to have a high quality training data before we can start to train the classifier, a new algorithm. In this case, you want to use only, for example, 9 out of 10 training data sets. Will you use 10% of your training data as a test? In that case, it's yellow. So you use the rest of 90% of your training data to train the classifiers, and then use your leftover, the 10% training data to test the trained classifiers. You do this one round and another round, use different fragments of this 10% of training data as a test. Then you found an average accuracy because you know the answer, right? You can compute the accuracy of your classifiers after training with 90% of data. So you repeat this 10 times and take average. Then you have average final accuracy, maybe 93% in this case. Is that clear? Okay. And I'm sure you know all this, that's accuracy or recall or sensitivity or specificity there. There's a definition of this. And you have this confusion matrix, which contains the numbers of your tested results. Either it's a true positive that you want to have a higher value here. That's the real positive, and you predict as a positive, correctly predicted, so that's a true positive. And also, if you have a actual, the real negative results, and then your prediction is negative, so you want to have a larger values in these two corners here. These two corners, true positive, true negative, and then you have false positive, false negative. Okay. To be good classifiers, you want to have smaller values in these two corners here. This confusion matrix that has those 4 numbers in there. This coefficient, Matthews correlation coefficients, also sometimes I saw that used in validation of some evaluation papers. Okay, ROC curve. So this is two-dimensional space defined by false positive rate. Okay. In x-axis, and in y-axis are the true positive rate. Sometimes people read using specificity as x-axis. You will see a lot of them. Specificity. If you decide to use specificity as your x-axis, you have to label this. Instead of from 0 to 1, you have to label from 1 to 0 in the reversed order, because you want to have a higher specificity on the right. left side. Okay, so once you, whatever, so because be careful to pay attention to x-axis, whether it's a false positive rate or specificity. Then the label of those values will be opposite. Anyway, you want to have a good results. This good results should be in your left top corner, somewhere here. The best result you can get should be those give you the high positive rate, true positive rate, and low false positive rate, somewhere here. And this point that in order to give a curve like this, so you cannot just compute just one data point. That's you train your classifiers and give the highest false positive and the true positive. Then on this plot, there's only a single point. That's not from the curve. So what you have to do is to find a way to change the parameter, for example, change the cutoff. For whatever reason, you search for this parameter space to change the outcomes of your classifiers. Sometimes it's good, sometimes it's bad. At the end, you will have a curve. So this curve should overall push to the up left corner. That's a good performance because your classifier is not so sensitive to the parameter space. So if you have a wrong estimate of one parameter, you still give relatively high true positive and low false positive, negative, false positive, because your whole curve shifts to the upper right direction. So this curve is informative. The way to measure this push to the the level of this push to the left up corner is to calculate the area under the curve. So you want to have a as large as possible area under the curve. That means your curve is push up and left, indicate classifier is performed really well and is not so sensitive to the options of the parameter combinations. Yeah, so roughly speaking, it's not so easy to construct such a curve because you have to make your classifier have some kind of variation performance in order to have multiple points in there to compute the curve. So this is really a good way to illustrate or to show people your classifier is working well. If it's a random classifiers and no power, you will expect some curve which close to this diagonal line, and the area under the curve is relatively small. So you don't want something like this. This will be very close to random. Random classifiers. Okay, I will mention a couple of these single cell classification tools, and I would say none of them work very well. The reason, again, it's because in biology we don't have good training data. Okay, people are still collecting more and more samples from different tissues and different disease states. New cell types just discovered. So there's no way you can have a beautiful, comprehensive ground truth data set. if that's the case, the better your classifier algorithm is, then your performance will be worse, because if your classifier is so sensitive to the ground truth of the training data set, then you have a poorly characterized training data set, then the outcome of your classification algorithm will be really bad. Some of these examples, people, I think I heard about this single R people use in selection, class level, experiment collection. Theory package using random forest. I don't know whether they changed it in the newer latest version of that, but still, that's two packages I have ever heard of. And I mentioned this one because it uses SVM. That's what we are going to discuss next week. There are papers to compute comparative studies to see, okay, the performance between different automatic cell type identification method. Yeah, so you see, you may recognize some of the algorithm people we just mentioned. LDA has been applied here. Mention this, mention that. Well, I just don't see any of them have been widely used. In the real study, we don't rely on this. We can use this automatic cell type identification algorithm as our first step to give you some idea, okay, what are the major group of those cells are. So we don't rely on this. So still, we don't have a perfect solution for automatic cell type identification yet. I hope we will. Well, so this algorithm, I just borrowed the pipeline illustration here, and this looks like it has a PCA in the middle here, and then separate cell type and select PC. So it's not using the top PC, but using the next level 2 and 3, because it found the separation of different cell types separated better in those combinations of PC, and then you select those PC rather than use the whole gene sets. Okay, see, I highlighted this. We need training data, so you have labeled them correctly. Okay, now you realize what they are doing here. You have this data, you know, you have your PC, extract the information which usable to separate the cells, and then you separate your training data into training part and the test part to do this cross validation several times. Okay. You obtained, evaluate your parameter selection, and then set up your best model. Best model means the best combinations of parameters for your training data. Well, once you have new data points, new cells come in and ready to be predicted for their cell types, you do the same thing. Project, use PCA and select the top PC and run through this nice model classification and decide the cell types. Yeah, so this is called the single cell net. Training data, single cell data, and from some user annotation. The borrow information from across a species. I don't know how this will be done. And do the training and some evaluation that is ready to be used to for the query data. It also contains some information, downstream analysis, okay, whatever. That's another applications. A lot of new algorithms just pop up daily. We may have at least 50 or even more this kind of applications, algorithms, we don't know. So at the end, I'm going to use this paper and we will look at its material and the method section. And for this particular section, it's called identification of cell type subtypes from single cell RNA-seq data. See how in the real applications, people deal with the situation. And I think today the manual annotation is still mainstream. And you don't want to completely rely on automatic annotation tools to give you the final assignment of cell types for your precious single cell data. So I'm going to switch to the paper, and it's published in Nature Medicine a couple of days ago. Ulcerative colitis, colitis. So this study, in this study, there are a lot of B cells in the section of methods. So I will jump directly to the methods. Okay. Oh, let's look at its figure 1, maybe. Yeah, I will jump directly to the methods. In the method, they first mention the cohort of patient, and then sample collection, intestinal cell isolation from the tissue, and the flow cytometry to enrich certain type of cells. Mass cytometry. expressions. Okay, so this section is single cell experiment. They use 10x genomics total. And then here are some of this basic analysis for clustering. Okay, here we go. Identification of T cell subsets. So they focus on the T cell subtypes. And then first, they use literature-based knowledge and their previous work and they define 5 gene expression groups. Okay. The first group is cell cycling. They use those marker genes. The second group is immune regulation. So they use those marker genes. Naive central memory T cells. Those group. CD8 cytotoxic T cells. So you have CD8A, certainly you have to have this expressed in the cell. So those marker genes. At the end, this is called resident memory T cells. So they use those marker genes and then for each cell, they just count, total UMI count for each of those combinations of the cell expression, gene expression. So for each cell, they will have 5 values, right? So that's figure. I think this B is what they, let's see. Oh, no, that's not one. Yeah, so this figure A is what they are results of this section. Duplicate. Oh. And let's see. Okay, so that's their result of a cell program. I mean, you can replace these 5 programs as a different cell type, the same idea, right? So if you think you have CD8 T cell, then you look at the profile of this marker genes total. You see this high value here indicate cluster 10 cells have the highest values relative to other programs. So those cells are most likely to be CD8 cytotoxic T cells. And it looks like cell cluster 11 have highest value compared to the rest class. And also compare across the programs, there are cycling cells in there. So that's the one way you can just look at a group of cells and just sum the total because you already normalized all the cells by for their library size. So relatively high total sum of the program will indicate those cells are involved in that process. So depending on how you define those, and there are other ways also to compute this score. In this case, it's a very simple, naive total sum of UMI for the marker genes for that program. There are some other ways to compute this score. Anyway, so basically that's the rough idea. And for cell type assignment, okay, we may spend some time later and read the rest of these paragraphs. Today, I just think we can just stop here. They use marker genes by manually check those expression, relative expression enrichment for each individual cell group as an average total. Right? Okay, that's all for today. And let me see whether anyone has any questions. All right, and see you Thursday in computer lab.